Welcome to this deep dive. Today, we're really getting into the nitty-gritty, laying the groundwork for radiation oncology by looking at how radiation actually interacts with cells.
Yeah, and specifically the damage it causes, particularly to DNA.
Exactly. Think of this as, well, your essential guide to the physics and biology that makes radiation therapy tick. It's pretty fundamental stuff.
It absolutely is. And, understanding these very first steps is so crucial for everything that follows: interpreting plans, figuring out responses, managing those side effects we see.
Right. It's not just theory.
Not at all.
Yeah.
So today we'll break down the types of radiation, how they deposit their energy, and what happens to the main target in the cell, which is, of course, the DNA.
Okay, let's dive right in then. What actually makes radiation ionizing? Is it just any energy?
Good question. Basically, ionizing radiation carries enough energy per packet, per photon or particle, to physically knock an electron out of its orbit in an atom or molecule.
Ah, so it creates an ion. Ionizing. Make sense?
Precisely. It's ionization. Lower energy stuff like visible light or, say, radio waves might jiggle electrons to higher energy levels. We call that excitation. But they don't have enough oomph to actually eject them.
Is there like a threshold number we should keep in mind?
Yeah. The sort of rule of thumb is energy greater than about 124 electron volts, or EV. That energy level corresponds to light with a wavelength shorter than about 10 to the minus 6 centimeters. Anything above that is generally considered ionized.
Okay, 124 EV. Got it. So in our field, radiation oncology, what are the main types of ionizing radiation we're actually using or concerned about?
We generally think about two main categories. There's electromagnetic radiation, and then there's particulate radiation.
Okay, let's start with electromagnetic.
Right. So in that category, we're talking about high-energy photons. The big players are X-rays and gamma rays. They're both packets of energy traveling at light speed, no mass, no charge.
But there's a difference in where they come from.
Right. Exactly. That's the key distinction. X-rays are generally considered extranuclear. They're produced outside the atom's nucleus. Think about our LANX. High-speed electrons hit a metal target, slam on the brakes, and that lost kinetic energy gets converted into X-ray photons.
Okay, electron interactions outside the nucleus. And gamma rays.
Gamma rays are intranuclear. They come from inside the nucleus. Usually it happens when an unstable atomic nucleus decays, settling into a lower energy state. It sheds that excess energy as a gamma ray photon.
So same type of energy packet, photon, just a different origin story.
You got it. Nuclear decay versus electron interaction.
What about other electromagnetic waves, like UV light? We know sunshine causes skin cancer, so that's damaging.
Ah, yes. Good point. Things like ultraviolet light, visible light, infrared, radio waves. They are all technically electromagnetic radiation, but they fall into the non-ionizing category.
But UV does cause biological damage, like you said, those pyrimidine dimers.
It absolutely does. UV causes things like thymine dimers, TT dimers, which are definitely biologically significant damage to DNA. But it does this mainly through excitation, causing photochemical reactions, rather than directly ejecting electrons like X-rays do. So, for board purposes and in the context of how we define ionizing radiation, UV light is classified as non-ionizing.
Okay, important distinction for exams. UV is non-ionizing, causes CT dimers. What about radio waves? Cell phones and whatnot.
Even lower energy. Based on, the current scientific consensus and evidence, radio waves are considered non-ionizing and not carcinogenic.
All right, so X-rays and gamma rays are our main ionizing electromagnetic players. What about the particulate side, actual particles?
Right, these have mass and they carry kinetic energy. The important ones for us include electrons, sometimes called beta-minus particles when they come from nuclear decay. They're small, negatively charged. We actually use electron beams therapeutically sometimes. Then you have protons, much heavier than electrons, positively charged, obviously the basis for proton therapy.
Right, big machines.
Yep. Then alpha particles. These are essentially helium nuclei, 2 protons, 2 neutrons, so they have a +2 charge. They're really heavy, deposit energy very densely, but they don't travel far in tissue. Radon gas, for instance, emits alpha particles.
Okay. Heavy hitters, short range.
Exactly. Neutrons are also important. They have about the same mass as a proton, but no charge. This lack of charge means they interact differently. They cause ionization indirectly, which we'll get into.
Interesting. No charge, but still cause ionization eventually.
Yeah. And finally, you can have heavy charged nuclei, basically, ions heavier than helium, like carbon ions. These are used in some specialized particle therapy.
Okay, quite a zoo of particles.
Yeah.
So all these different types Photons and particles, they hit our tissues. How does that energy actually get deposited to cause, the biological damage?
It all comes down to interactions at the atomic level. We can classify how the initial ionization happens as either direct or indirect ionization.
Okay, direct versus indirect ionization. Let's start with direct.
Direct ionization is caused by charged particles. So electrons, protons, alpha particles, those heavy ions we mentioned. Because they have an electric charge, they directly interact with the orbital electrons of the atoms they pass near. It's basically the Coulomb force attraction or repulsion that just knocks those orbital electrons out.
They're like a bowling ball hitting the pins directly.
That's a great analogy. Yeah, the charged particle is the bowling ball, and the orbital electrons are the pins. Direct hit, pins scatter. Creates a trail of ions right along the particle's path.
Okay, that makes sense. So what about indirect ionization then? That must be the uncharged ones.
Exactly. Indirect ionization is the mechanism for uncharged radiation. So photons are X-rays and gamma rays and neutrons. Because they don't have a charge, they don't really interact strongly with orbital electrons just by passing by.
So how do they cause ionization?
They have to do it in 2 steps. First, the uncharged photon or neutron has to transfer some or all of its energy to a charged particle within the tissue. Then it's that secondary charged particle that actually goes on to cause the direct ionization, just like we discussed.
Okay, so it's a handoff.
A handoff, precisely. The uncharged particle starts the process, but a charged particle finishes the job of ionization.
Let's dig into that handoff. How do neutrons do it? They have no charge, they have mass.
Right. Since they're uncharged, they don't interact much with electrons. Instead, they tend to interact with atomic nuclei. Now, tissue is mostly water and organic molecules, so it's very rich in hydrogen.
Hydrogen nuclei are just protons.
Exactly. So a very common interaction is the neutron essentially colliding with a proton, a hydrogen nucleus, transferring a significant chunk of its kinetic energy to that proton. This proton gets knocked forward. We call it a recoil proton.
And that recoil proton is charged.
Bingo. That energetic recoil proton is now a charged particle moving through tissue, and it causes direct ionization along its path. Neutrons can also interact with heavier nuclei like carbon or oxygen, sometimes causing them to break apart and release charged particles like alpha particles, which then cause ionization too.
So the neutron starts a chain reaction, producing charged particles that do the ionizing.
That's the essence of it for neutrons. Indirect ionization via charged particle production.
Okay. Now, what about photons? X-rays and gamma rays. How do they hand off their energy? This is super relevant for standard therapy.
Absolutely. Photons, being uncharged, transfer their energy primarily to electrons in the tissue. There are 3 main interaction processes we need to know, and which one dominates depends heavily on the photon's energy and the type of tissue.
Okay, 3 processes. What's the first one?
The first is the photoelectric effect. This is more important at lower photon energies, like those we use in diagnostic imaging, maybe low-energy brachytherapy seeds too.
Okay, photoelectric. What happens?
Here, the incoming photon interacts with a tightly bound inner shell electron, usually in the K or L shell. The photon gives all of its energy to that electron, ejecting it from the atom. The ejected electron is called a photoelectron.
And the photon.
The photon completely disappears. It's absorbed. Now, this leaves a vacancy in that inner shell, which is quickly filled by an electron dropping down from a higher shell. That drop releases energy, often as a characteristic X-ray or an Auger electron.
Right. And this effect depends on the material.
Very much so. It's strongly dependent on the atomic number Z of the absorber material, roughly proportional to Z cubed. It's also more likely at lower photon energy. This Z dependence is why bone, higher Z than soft tissue, shows up so well on diagnostic X-rays and why we use high Z materials like iodine or barium for contrast.
Okay, so photoelectric effect. Low energy, high Z, photon absorbed, inner electron ejected. Key for imaging contrast. Does it matter much at therapeutic energies, like 6 MV?
It still happens, but it becomes much less dominant in soft tissue compared to the next process, especially at megavoltage energy.
Okay, so what's the dominant process for therapy?
That would be the Compton effect, or Compton scattering. This is really the workhorse interaction for dose deposition in soft tissue when we're using typical therapeutic X-ray beams. The megavoltage range from about a few hundred keV up to many MeV.
Compton scattering, how does that work?
In this case, the incoming photon interacts with a more loosely bound outer shell electron. Instead of giving all its energy, the photon transfers only part of its energy to the electron, ejecting it from the atom. This ejected electron is called a Compton electron.
And the photon doesn't disappear this time?
No, it doesn't. The original photon continues on, but in a different direction. It's scattered and with less energy than it started with.
So you get an ejected electron and a scattered lower energy photon?
Exactly. And both of those can potentially go on to cause further ionizations or interactions. The Compton effect is less dependent on the atomic number of the tissue compared to the photoelectric effect, especially at higher energies. It mainly depends on the electron density of the material, which is pretty similar for most soft tissues and water.
Which is why dose distribution is relatively uniform in soft tissue at therapeutic energies.
That's a big part of it, yes. But it also means scatter is a major consideration in treatment planning. We have to account for where those scattered photons might go.
Okay, Compton effect. Main interaction at therapeutic energies, partial energy transfer to outer electron, photon scatters with lower energy.
Got it.
What's the third photon interaction?
The third one is pair production. This only happens if the incoming photon has a very high energy. Specifically, its energy must be greater than 1.022 MeV.
Why that specific number, 1.022 MeV?
Well, that relates to Einstein's famous E/mc squared. 1.022 MeV is the energy equivalent of the rest mass of 2 electrons, 1 electron and 1 positron. It's antiparticle.
Okay, so what happens?
The high-energy photon interacts strongly with the electromagnetic field near the nucleus of an atom. In this interaction, the photon's energy is converted directly into mass. It creates a pair of particles, an electron and a positron. The photon disappears in the process.
Wow. Energy into matter. E/mc squared in action.
Pretty much. Now, that newly created positron doesn't last long. It's antimatter. It travels a very short distance, loses energy, and then bumps into an electron.
And they annihilate.
They annihilate each other. Their mass is converted back into energy, typically producing 2.511 MeV photons that travel off in opposite directions.
0.511 MeV. That sounds familiar. Isn't that what PET scanners detect?
Exactly. That annihilation radiation is the basis of PET imaging. We give patients a tracer with a positron-emitting isotope, and the scanner detects these pairs of 0.511 MeV photons coming out.
Cool connection. So pair production becomes important only at really high energies.
Yes, generally above 10 MeV, and it becomes increasingly significant as the energy goes up, say towards 18 or 20 MeV and beyond. It also depends more strongly on the atomic number of the material than Compton scattering does.
Okay, so to recap ionization, charged particles do it directly. Uncharged photons and neutrons do it indirectly by first creating secondary charged particles, electrons for photons, recoil protons or alphas for neutrons, and those do the direct ionizing.
You've got it. That's the physics of the initial energy deposition.
Now let's shift focus. We've got these ionization events happening. How does that translate into damage to the critical parts of the cell, especially DNA?
Right. So now we talk about direct action and indirect action again, but this time referring to the biological mechanism of damage, specifically to the DNA molecule, which we consider the principal target for radiation-induced cell killing and mutation.
Okay, direct action on the DNA. What does that mean?
Direct action means the ionizing radiation itself, whether it's the initial charged particle like a proton or a secondary electron set in motion by a photon, physically scores a direct hit on the DNA molecule.
Like it actually ionizes or excites an atom within the DNA structure.
Exactly. It could hit a sugar, a phosphate in the backbone, or one of the bases. The energy gets deposited right in the DNA, causing immediate chemical changes, bond breaks, alterations right there.
Is this common?
It's the dominant way that high LET radiation causes damage. ALET stands for linear energy transfer, basically how much energy the radiation deposits per unit distance it travels.
So things like alpha particles, neutrons.
Yes, alpha particles and the recoil protons produced by neutrons are high LET. They dump a lot of energy in a very short track, like little bombs going off. Because they deposit energy so densely, the chance of them directly hitting the relatively small DNA target is much higher.
Okay, high lead radiation, dense ionization, more direct hits on DNA.
That's the idea.
So what's indirect action in the biological sense, if it's not hitting the DNA directly?
Indirect action involves a middleman. The radiation first interacts with other molecules near the DNA, and the most abundant molecule by far in a cell is water. Cells are about 80% water.
Okay, so the radiation hits the water.
Predominantly, yes, especially for low LET radiation like X-rays and gamma rays. When radiation ionizes a water molecule, it creates highly reactive chemical species called free radicals.
Free radicals, those sound bad.
They are in this context. These free radicals are unstable molecules with unpaired electrons, making them eager to react with whatever they bump into. They can diffuse a very short distance from where they were created.
And if they bump into DNA?
If they diffuse that short distance and encounter a DNA molecule, they can attack it chemically, causing damage, breaks, base alterations, etc. So the radiation hit the water produced a radical, and the radical damaged the DNA. That's indirect action.
Can you walk us through that water chemistry? How are the radicals made?
Sure. It's called the radiolysis of water. When radiation hits HO, it can knock out an electron, leaving a positively charged water ion, HO, and the free electron, E.
All right.
That HO is unstable and very quickly falls apart into a hydrogen ion, HO, and a hydroxyl radical, which is written as OHO. That dot represents the unpaired electron, making it a radical.
Okay, so we've got the hydroxyl radical, OHO. What about the electron that got knocked out?
Good question. That free electron, E, can also react with another water molecule, creating a negative water ion, HO. This is also unstable and quickly breaks down into a hydroxide ion, OHO, which is stable, and a hydrogen radical.
So we get hydroxyl radicals, OH, and hydrogen radicals plus some ions.
Primarily, yes. There are other minor products too, but those radicals are the key reactive species.
And which one is the biggest troublemaker for DNA?
The hydroxyl radical, OHO, is considered by far the most important for causing biological damage via indirect action. It's a powerful oxidizing agent, extremely reactive.
Why is it more important than, say, the hydrogen radical?
It's just chemically more damaging to biological molecules, and while its lifetime is short, it's perhaps slightly longer or more likely to react damagingly than some of the other species generated. It's responsible for the majority of the indirect damage.
But you said they have to diffuse to the DNA and they're super reactive. How close does the water molecule have to be to the DNA when it gets hit?
That's a really critical point. These radicals get neutralized or scavenged very quickly by reacting with other molecules around them. So for an OH radical to damage DNA, it has to be generated very close by.
How close is very close?
We're talking nanometers. The estimate is that the water molecule needs to be within the hydration shell of the DNA, the layer of water molecules immediately surrounding the DNA helix. That's a radius of only about 2 nanometers. If the radical is formed further away than that, it's highly likely to react with something else before it ever reaches the DNA.
Wow, tiny distance. So indirect action is really a very localized effect, even though it starts with water.
Exactly. It has to happen right next door to the DNA.
And you mentioned this is dominant for low LET radiation, like our standard X-rays.
Yes, that's right. Low LET radiation, like X-rays and gamma rays, deposits its energy sparsely along its track. Think of occasional ionization events spaced relatively far apart. Because water is so abundant compared to DNA, the probability of one of these sparse ionization events happening in a water molecule right next to DNA is much, much higher than the probability of a direct hit on the DNA.
So most of the damage from X-rays comes from these hydroxyl radicals attacking the DNA.
Estimates are that for low LET radiation, about 2/3 of the DNA damage is caused by indirect action, primarily via OH radicals. The other 1/3 is from direct action.
2/3 indirect, 1/3 direct for X-rays. That's a key ratio.
It is, and it leads to an interesting experimental observation. If you irradiate DNA when it's dry, completely free of water.
Then you only get direct action. No water, no radicals.
Precisely. And you find that you need a much higher dose of low LET radiation to cause the same amount of DNA damage in dry DNA compared to DNA in a normal aqueous solution. It demonstrates the significant contribution of that indirect effect.
That makes perfect sense. Okay, so whether it's a direct hit or an indirect attack by a radical, what kinds of damage actually happen to the DNA molecule itself? What are the lesions?
There's quite a spectrum of damage. Probably the most frequent type of lesion is base damage.
Damage to the A's, T's, C's, and G's.
Yep. This can be a chemical modification, like oxidation, think of 8-hydroxyguanine, that's a common one, or other alterations. Or the base can actually be lost entirely, leaving in a basic site or AP site in the DNA strand. Damage to the hydrogen bonds holding the two strands together can also occur.
Are these base damages a big problem for the cell?
They're very common, but generally the cell has pretty efficient repair pathways for them, mainly base excision repair, or BER. We'll talk more about repair later, but BER is good at fixing these smaller base lesions.
Okay, base damage is frequent, but usually fixable.
Yeah.
Who else?
Then you have breaks in the sugar phosphate backbone. You can get a single strand break, or SSB.
Just one strand of the double helix is broken.
Right. The backbone is cut on one side, but the other strand is still intact. These are also quite common, maybe around 1,000 SSBs induced per cell per gray of low LET radiation.
1,000 per gray. Wow. But are they lethal?
Generally, no. Because the other strand is intact, the cell can usually use that as a template to accurately repair the break pretty efficiently. However, sometimes the break can have damaged ends, maybe from oxidation, which can make the repair a bit trickier for the standard SSB repair pathways.
Okay, SSBs are common, usually repaired using the template strand. Now, what about the ones we always hear, the really bad ones?
Yes. You're talking about double-strand breaks, or DSBs. This is when both strands of the DNA helix are broken and the breaks are close to each other, typically defined as being within about 10 base pairs on opposite strands.
Both strands broken nearby. Why is that so much worse?
Well, think about it. With an SSB, you have the intact opposite strand to guide the repair. With a DSB, the entire helix is severed. There's no immediate template right there to ensure correct rejoining. The broken ends can drift apart, potentially leading to loss of genetic information. Or the cell might try to stick the wrong ends back together, leading to things like chromosomal translocations or inversions.
Okay, that sounds much more dangerous. Loss of information, incorrect rejoining.
Exactly. That's why DSBs are widely considered the most critical lesion for radiation-induced cell killing, mutation, and carcinogenesis. They are the major challenge for the cell's repair systems.
How common are DSBs compared to SSBs or base damage?
Much less common. For every gray of low LET radiation, a cell might get around 40 DSBs. Compare that to the 1,000 or so SSBs and even more base damage.
So 40 DSBs per gray, less frequent but much more consequential.
Precisely. And the cell has dedicated complex pathways to try and fix these DSBs, like non-homologous end joining, NHEJ, and homologous recombination HR, which, as you said, we'll definitely cover in a future deep.
Okay, base damage, SSBs, DSBs, any other types of damage?
We can also see cross-links forming, though they're generally less common with ionizing radiation compared to, say, certain chemotherapy drugs. You could get cross-links between bases on the same strand, intrastrand, or between the two opposite strands, interstrand, or even between the DNA and proteins bound to it.
Less common, but probably hard to repair too.
They can definitely interfere with replication and transcription, yes. And one other category worth mentioning, especially concerning high LET radiation, is what we call multiply damaged sites or clustered lesions.
Clustered lesions, what's that?
This refers to a situation where you get multiple types of damage, maybe a DSB, a couple of nearby SSBs, and several base damages, all occurring within a very small region of the DNA, just a few nanometers or maybe 10, 20 base.
So like a concentrated zone of destruction.
Kind of, yeah. These are thought to result from a single high LET particle track passing through or very near the DNA, dumping a lot of energy and causing multiple damages simultaneously in that tiny volume. As you can imagine, these complex clusters are particularly difficult for the cell's repair machinery to handle accurately.
Makes sense. So if we had to rank them, frequency versus biological significance.
Okay, for frequency after low LET radiation, it generally goes. Base damage is the most frequent, then single-strand breaks, then double-strand breaks are the least frequent of those three.
Base, SSB, DSB for frequency.
Right. But for biological consequence, or lethality, it's pretty much the reverse order. Double-strand breaks are considered the most critical and potentially lethal lesion. Then SSBs, which can be problematic if not repaired properly or if complex. And then base damages are generally the least cytotoxic, although they can be mutagenic if misrepaired.
So DSB, SSB, base damage for biological significance.
Exactly. The frequency doesn't tell the whole story. You can use the car analogy. Base damage is like a paint scratch, annoying, frequent, but usually fixable without stopping the car. And SSB is like a flat tire, more serious, needs repair, but you have a spare, the template strand. A DSB is like, I don't know, throwing a rod in the engine, catastrophic, hard to fix, might total the car or the cell in this case.
That's a helpful way to think about it. DSB is the engine failure.
Yeah.
And it's important to remember this spectrum of damage from ionizing radiation is different from, say, UV damage, right? We touched on that.
Absolutely crucial distinction. Ionizing radiation gives you this mix of base damage, SSBs, DSBs, maybe some clusters. UV light, on the other hand, its signature damage is those bulky pyrimidine dimers, like the TT dimers, and another lesion called a 6,4 photoproduct. Ionizing radiation doesn't really make those.
Different damage, different repair pathways.
Totally different repair. The bulky lesions from UV are primarily handled by nucleotide excision repair, NER. The damage from ionizing radiation uses base excision repair, BER. single-strand break repair, SSBR, and the DSB repair pathways, NAGJ and HR. Understanding which pathway fixes what damage is key later on.
Okay, this is a great foundation. We've covered the physics of interaction, the chemistry of radicals, the types of DNA damage. How does all this connect back to our daily work in the clinic?
Oh, it connects everywhere. Think about diagnostics. That photoelectric effect's dependence on atomic number Z. That's why bone, higher Z, looks white, and lungs, low Z air, look black on an X-ray or CT scan. That's also why iodine contrast, high Z, works so well.
Right. Basic imaging principles rely on this.
Absolutely. Then in therapy, the dominance of the Compton effect at megavoltage energies is fundamental to how we deposit dose in patients using photons. It dictates penetration, scatter, and why tissue density matters more than atomic number for dose calculations in that range.
And the indirect action, the hydroxyl radicals.
Huge clinical relevance there. That leads directly to the oxygen effect. Molecular oxygen is a fantastic radiosensitizer, especially for low-light radiation. It reacts with the initial DNA radicals formed both by direct and indirect action and essentially makes the damage permanent or fixes it, preventing chemical repair.
So tumors that are hypoxic, low in oxygen,
are significantly more resistant to radiation. That's a major challenge in radiotherapy. Understanding the role of oxygen and indirect action helps explain why things like hypoxia imaging or dose escalation strategies are being explored.
Wow, okay. And the DNA lesions themselves, especially the DSBs.
Knowing DSBs are the critical lethal lesion is paramount. It explains why patients with inherited defects in DSB repair genes, think BRCA1, BRCA2 associated with homologous recombination, or ATM involved in signaling and NHEJHR, can have dramatically different responses to radiation, both in terms of tumor control and normal tissue toxicity. Their cells just can't fix the most important damage properly.
So understanding the basic damage links to personalized medicine and predicting toxicity?
Definitely, and it also explains why high-LET radiations, like protons near the end of their range, the Bragg peak or carbon ions, have a higher relative biological effectiveness, or RBE. They cause more direct damage and more of those complex clustered lesions, including DSBs, which are harder to repair, so you need less dose to achieve the same biological effect compared to LIT.
Okay, the connections are really clear. This basic science is not just basic, it's essential. Let's try to boil this down now. What are the absolute must-remember points from today for, say, board review?
All right, must-remember points. Here we go.
Ionizing radiation has enough energy, think 124 eV, to eject electrons. X-rays, gamma rays, electrons, protons, neutrons, alphas, they're ionizing. For boards, UV light is generally not considered ionizing in our context. It causes TT dimers.
Got it. Ionizing versus non-ionizing, easy.
Second, know the origins. X-rays come from extranuclear electron interactions. Gamma rays come from internuclear decay.
X-ray extra, gamma intra.
Okay. Third, DNA damage happens via direct action, radiation hits DNA, and indirect action, radiation hits water, base for re-radiated Newton interest DNA.
Direct versus indirect action on DNA.
Fourth, for low-LET radiation like X-rays, indirect action dominates, accounting for about 2/3 of DNA damage. The main player is the hydroxyl radical, OHA. And remember, less damage happens in dry DNA because there's no indirect action.
Low-T,
Yeah.
mostly indirect via OHA, needs water.
Fifth, remember the DNA lesion hierarchy? Frequency, base damage, SSB, DSB. But biological significance allality, SSB base damage. Double-strand breaks are the most critical for cell killing.
Frequency versus significance. DSBs are the killer lesion. Perfect. All right, feeling ready. Let's do a quick board review blitz to hammer these home.
Let's do it. Question 1. Which of the following is not considered ionizing radiation in the context of radiation oncology board examinations? A, gamma rays. B, alpha particles. C, fast neutrons. D, ultraviolet light.
Okay, we just covered this. UV light is the non-ionizing one here for boards, so D.
Correct. Question 2. The indirect action of clinical megavoltage X-rays primarily mediates biological damage through A, direct ionization of DNA by the incident photon. B, heat generation within the tissue. C, the production of hydroxyl radicals from water radiolysis. D, interactions with the nuclear membrane.
That's the water radiolysis story. Production of hydroxyl radicals. C.
Spot on. Question 3. Following exposure to 1 gray of low LET radiation, which type of DNA lesion is induced most frequently in a cell? A, double-strand breaks. B, single-strand breaks. C, DNA-protein crosslinks. D, base damage.
Frequency hierarchy. Base damage is number 1. D.
Excellent. Last one for this round. Question 4. Which type of DNA lesion is generally considered the most critical determinant of cell killing by ionizing radiation? A. Base damage. B. Single-strand breaks. C. Double-strand breaks. D. Pyrimidine dimers.
The critical one for killing, that's the engine failure, the double-strand break.
You nailed it. Fantastic. So that wraps up our deep dive today into the very first steps, how radiation interacts physically and chemically, and the initial damage it inflicts on DNA.
Yeah, we covered a lot. Ionizing radiation definition, the different types, direct versus indirect ionization with photons and neutrons, then direct versus indirect biological action on DNA, focusing on that crucial hydroxyl radical.
And we finished up with the whole spectrum of DNA lesions, from base damage right up to those critical double-strand breaks and clustered lesions.
So next time, we're going to pick up right where we left off and explore how the cell actually fights back the amazing world of DNA repair mechanisms. We'll start with how cells fix those common base damages and the bulky lesions we mentioned, looking at base excision repair and nucleotide excision repair.
It's a fascinating story of cellular defense. Definitely join us for that next deep dive. Until then, keep thinking about those radicals.